the meaning of a joule of work. After the lab, you might have a feel for what I'm going to be talking about. But I think that we should really step back and look at it just a little bit more carefully. So here we go. So what we know here is that work and energy units are in joules. But in the United States, we use calories. So the imperial unit of energy is a calorie. And it turns out that there are 2 calories. There's what we call a little calorie. So a little calorie goes by the symbol little c, and that's equal to 4.186 joules. It's a tiny, tiny bit here. And in everyday situations, we never use the little calorie. But then we have the so-called big calorie. And a big calorie is the same as one big cal, one big C, and it turns out to be 1,000 little C's, and this is equal to 1 food calorie. So a big calorie is a food calorie, and this guy is equal to 4.186 times 10 to the 3 joules. And so this is what the standard unit. So I would say that this is the standard unit of everyday situations. We measure things in food calories. So to give you a sense of what do we mean by what is a joule here, I want to do a calculation. So I hear this all the time, and maybe what we want to do here is that we want to think about the following thing. So suppose you go to McDonald's I think that's the way you spell McDonald's. You go to McDonald's and purchase a chocolate shake. And I looked it up. The chocolate shake has a mere 1,160 food calories. And that's a whopper. That's a lot of calories right there. Right? That's a lot of calories. So then a very common statement that you hear people say is that afterwards, you drink it, one feels guilty. and feels the need to work it off. So, what does that mean? So, as an example, the only thing I'm going to do here is, just because this is a nice example, I could have picked a soda, by the way. That would have worked just fine, right? It has 150 calories. Like, you can Google that, and it's about 150. They vary a little bit. But now what you're going to do here, so to work it up, what you're going to do here is that you're going to bench press. You're going to bench press 160 pounds, and that turns out to be 710 newtons. Okay? You're going to bench press 160 pounds. So now the question is this: how many times must you lift the bar to work off the milkshake calories? And we already said that that milkshake calories is this guy right here. So let's go look at that. So what I did here is that I just took a tape measure and I started looking at what I would have to do. So it turns out, so if this was Carlos lifting the bar, what actually happens here? So what happens here is that you could imagine that I have a bar. Here's my barbell. So when I'm looking at my barbell, what I'm going to do here is that I'm going to apply a force upwards like that. So in this situation, we can clearly see here is that I have a displacement that goes that way, and then I'm going to lift it up to that height right there. So if I'm using Carlos, what I'm finding here is that when I lift up, I'm finding that the distance that I move it is 0.65 meters. So I'm essentially going from my chest to when I fully extend above my chest. So when you're looking at this thing, we can clearly see that if I think of Carlos, Carlos is the system here, right? So in this case, you could imagine that I have a bench press. And so here I am right here with my feet. And then here's where I'm lifting up the bar. So when I'm looking at this, what is my system? My system is my body. And then what you're seeing here is that there is an external force. There is the force of gravity acting downwards, but to compensate for gravity, I have to apply a force up here. So in this situation, you can see that my body does positive work on this bar in the lifting phase. So when I'm looking at this lifting phase, this is what it's telling me. That here, that my body does positive work on the bar. So then the work in this case on the on the bar is then going to be my force times my displacement in this case. That quantity is going to be positive. So when I look at this, then the work up will then be this force, which will be 710 newtons times 0.65 meters. That tells me that I did positive 460 joules. In other words, the work up on the bar is 460 joules, like that. This is positive work. But now, what happens when I lift it down? So now, if I, in the lowering phase, what actually happens here? Well, I have my bar, which is right here. Now I got to bring it down. What about my force? What do I know about my force? Well, I still have to push up, right? I don't want to apply a force downward because then I'm going to hurt myself. But the big difference here is that I'm lowering it, so the displacement is negative here. It's opposite. So if I do this, what I'm seeing here is that my body does negative work on the bar. So if I now look at the bar, again, this is going to be F times D, but this is negative. So then the work down is going to be the exact same calculation, but it's going to be negative 460 joules. So now, if I look at the work done on the bar, I'm then going to say that the net work is going to be the work up plus the work down. And if you look at this thing, here's what I'm seeing here. I'm going to get positive 460 joules minus 460 joules, which is 0. So in other words, there is no change in energy on the bar. Now, does that make sense here? The answer is yes. Because look what happens. The bar starts here. And it goes up. And then what does it do? It comes back down. So when I'm looking at the bar, what I'm seeing here is that from here, there is no net displacement. During the lifting of the bar. Therefore, even though there might be a net force, that displacement right here, this guy is 0. So therefore, the work is 0, and so therefore, the change in energy on that bar is 0. But the human body does work. So when you look at the human body, how is it that the human body does work? Well, when we say the work done by a body, by the way, in everyday language, what do we call this? We call this working out. What do we mean by working out? You apply a force. So your heart applies a force to your blood. And then what happens? Your blood moves a distance inside your body. And this is what happens to the work done by the body here. There's zero work on the bar, but your body does work. So now, if you look at, so how much work was done by the body? Well, the net work done by the body is going to be the work up plus the work down, but they're both positive. So in other words, this is the same as going up or down. So in this case, this will be 2 times 460, which will then gives me 920 joules, which I will go to 1 sig fig of 1,000 joules. And I'm going to say this is the work of the body. So now, what does this do here? So now what we want to do here is that we need to do a conversion factor. Okay. So now what I want to do is that I need to convert joules into calories. So I want to convert how much one lift burns in calories. So if I have 920 joules, I'm going to approximate that to 1,000 joules. Now, it turns out that I have 4,200 joules is the same as 1 food calorie. That's the conversion factor right there. And if you look at this thing, if you convert that, this gives you 0.238 calories. By the way, when I look at this thing, what I'm really doing here is that I've been carrying sig figs all along, but what this really equals to, I would then go and approximate that this is essentially 0.2 calories. So in other words, lifting 160 pounds only burns off 0.2 calories of the milkshake. So then, how many reps are required to burn off the milkshake? Well, here we go. So I would say then that the number of reps to burn off the milkshake should then equal what? It should equal that I have 1160 calories divided by 0.238 calories, and this roughly equals 4,900 reps. In other words, about 5,000 reps. That's a lot of reps to burn off a milkshake. But this is a bit of an exaggeration. Okay, the reason why this is an exaggeration is that immediately your body takes 25% of these calories to operate your body functions. And believe it or not, most of them go to your brain. So what you'll find here is that after the 25% reduction, so then if I go 4,900 reps, and then I take 25% of those calories off, you get 3,700 reps, which is ridiculous amount. Now, I'm no expert on whether you should be counting calories, because I know that I'm sure you guys know a hell of a lot more than I do. But for some people, counting calories really does make a difference. And, a small calculation like this, shows you that that is the case here. But again, this is complicated stuff. So I am no expert, and I am not going to think about it more than that.